All right, folks. So today our video is going to talk about optimization. All right, and optimization basically is maximizing or minimizing something. It's trying to get the most or the least out of something, giving specific constraints that we have. So we'll go through a bunch of examples of that today and talk about those different things, and then what we are trying to do, whether that is maximizing or minimizing based on the information that we are given. So this page here will show you the steps that we're going to go through for each of these problems to get to our optimized solution, and we'll follow these steps for all the problems. So just to go through, draw an appropriate sketch. Drawing is always a good way to visualize what's happening and to label the things that you know that you have. Identify an optimization equation. Essentially, that's the equation, the thing that you are trying to either maximize or minimize. It might be volume. All right, you're trying to get the most volume out of something. It might be the area. You're trying to minimize the amount of material that you use to make a box or a can or something like that. So that is, so whatever that ends up being, that is what you're optimizing. All right. What are your constraints? Okay. So the constraints are, what are the things that are holding you back from just making something as big as you want it to be or as small as you want it to be? And again, that could be things like, all right, I want to make a box, but I only have a certain amount of material. So my constraint is the amount of material that I have because it keeps me from just making the box as big as I want it to be. Then you use those constraints to rewrite your optimization equation. All right. So I'll talk about that when we do that in the example. Finding critical numbers, all right, remember finding critical numbers involves us having to take the derivative, setting the derivative equal to 0, and then solving for the x or whatever it is, the variable that we're looking for. Those critical numbers, all right, are important because they tell us where the maximums and the minimums are. So if we're trying to optimize something and find and maximize or minimize something, knowing those locations where those critical numbers happen, where we have a horizontal tangent line with a slope equal to 0, that's the important areas that we need to know to be able to optimize. Problem should look familiar. This is the one that we asked you guys to try and figure out on your own, to optimize the volume, maximize the amount of volume you can get out of a flat piece of cardboard by turning it into an open box, so a box with no lid. All right, so basically to do that, I drew a picture of what's actually happening. The X, it's an 18 by 18 sheet of cardboard, and then the X's are what you would be cutting out from each of the corners to be able to fold it up, right? Which would be, it would be folded along those dotted lines, all right, to make this box that you see below it with an open top, okay? So what is that X value that I would have to cut out from either side, top and bottom, all right, to be able to fold it up, have myself a box, all right, that has the most amount of volume that I could possibly get out of it, given the fact that I only have an 18 by 18 sheet of cardboard. All right, so there's my sketch. That'll be step number one. And then what we're going to do is we're going to identify the equation that we need and then the constraints that we have and go from there. Your next step is to find your optimization equation and what your constraints are. So my optimization equation is clearly my volume because I want to maximize the amount of volume I can get out of this 18 by 18 sheet of cardboard. All right, so the volume of any box is its length times its width times its height. And what I did was I turned them into all the same variable, meaning all in terms of x. It could be any variable, but I'm going to use x here so that I can work with this equation. If I had three variables, I would need three equations to be able to work through it. But if I turn it all into one variable, I can work through it with just the one equation. So that's what I'm going to do. All right, and what you'll see is I did that here is 18 minus 2x. Well, what is that? Okay, so the 18 minus 2x is the 18 original flat dimension. Cutting x from either side means I'm taking two, whatever that x turns out to be, from either side so that I can fold it up and turn it into a box. And for both dimensions, both are 18, I'm taking two x's away from either side of that 18 to be able to fold it up and turn it into a box. So my length would be 18 now minus 2x to fold it up, 18 minus 2x's on either side to be able to fold it up. And now what's the height of the box? Well, the height is whatever it is that I cut out, that x piece that I cut out, I'm now folding that up. That now becomes the height of the box. Okay, and then you'll see I just did the math here. I multiplied this all together to get it into a nicer version of that equation to be able to deal with. All right, so my volume in terms of x is that. That's my optimization equation. That's what I'm going to try and maximize. Okay, my constraint here is basically the cardboard that I have. And in this case, the cardboard is 18 by 18 inches. So what would be the actual number constraint of that? Well, basically, you end up having to have an x value that is somewhere between 0 and 9. If it's 0, that means I'm not cutting anything. I'm not turning it into a box. If it's 9, I'm cutting too much because I would cut 9 from each side. That takes away the entire 18. There would be, be no bottom of the box. I wouldn't have a box. So it has to fall somewhere in between those two numbers, all right, my value. And you'll see when I go through the process of optimizing here, that'll start to make a little bit more sense as to having the number fall in between those two. Okay, so the next step in the process is after I have this equation, I have to go ahead and I'm trying to find the critical values, trying to find the maxes or the mins, in this case, the max. So the max occurs at a critical value, which I find by taking the derivative of that equation. Okay, so the derivative of this equation, sorry, this should have an x here, should be squared, turns out to be 324 minus 144x plus 12x squared. Okay, and that comes from just doing the simple power rule. To find the critical values, I take that and I set it equal to 0. Set it equal to 0, my derivative, and I solved it, and you'll notice that I got two answers when I solved it, and one was 3 and one was 9. Remember, we said one of our constraints was that it has to be less than 9. So 9 we know will not work here because if I cut 9 from each side, I'm ending up folding the cardboard on top of itself and it doesn't end up being a box. Okay, so how do I know that the 3 is my maximum? Well, that's where our number line comes in. If you remember when we did maxes and mins, we tested points in the first derivative to see where this function was increasing and decreasing. Okay, that's what I'm doing here. I'm just figuring out, okay, when I test a point between 0 and 3, 3 being my critical value there and 0 and 9 being my endpoints, when I test a value like 1 in there, what do I get? Well, I get a positive number. I'm going to have positive numbers in there, positive slopes. So that means on that side of 3, it's increasing. When I plug a number between 3 and 9 in, like 4, I get a negative number. It's a negative 60. So on the other side of that 3, it's decreasing. So as I approach 3, I'm increasing. As I come away from 3, I'm decreasing. That means that I'm going like this, up, and then back down. That would show that that is a relative maximum point there, which is what I was trying to find. I was trying to find the maximum cut that I would need to make, that I could make to maximize my volume. All right, the cut that I'm going to make, the x is equal to 3 inches. I know that at that point I will find my max volume when I cut that amount from either side of the box. Okay, so that's what I put here. You have a 3-inch cut that you are taking out of the box. Okay, and then what kind of volume will that give you? What's my max volume now that I know that it's 3 inches that I need to take out from either side? I plug that 3 back into my volume equation. All right, and you can plug it into this version of it or this version, it doesn't matter. All right, you plug that x value in there. When you plug it in, you end up with a maximum volume of 432 units cubed. You just optimized the amount of space, you maximize the amount of volume for that in that box given the constraint of an 18 by 18 piece of cardboard. Okay, it doesn't have to be an 18 by 18 square, it can be anything. All right, and you can use this same process to figure out no matter what size piece of, or what piece of cardboard that you have size wise. Okay, you can use this same format or this same process to help you come up with what is the cut that's going to be needed to make from either side to maximize my volume. Okay. All right. The next problem is asking me to make a garden in a rectangular area protected by a fence, and then what is the largest possible area of the garden if I only have 100 feet of chicken wire available? Okay, so there's two things going on here. All right, and you'll see that I kind of wrote it all down already. Largest possible area. That's what I'm optimizing. That's what I'm trying to find. I'm trying to maximize that area. Why? Because it's saying largest possible area. So that's what I wrote down as my optimization equation. It's a rectangle, so I have an area maximum that's going to be L times W because that's the equation for the area of a rectangle. Okay, and then it gives me a constraint. The constraint is I only have 100 feet of chicken wire. All right, the unit should give this away here. That's just perimeter. 100 feet of chicken wire means I have a perimeter fence that can only be 100 feet long. That's as much material as I have to maximize my area. So you'll see here the C represents my constraint. My constraint is 100 feet of chicken wire to go around that entire rectangle, 2 lengths and 2 widths, the perimeter of that rectangle. So I only have 100 feet to go around and cover the 2 lengths and the 2 widths. All right. And then what I ended up doing was just kind of rewriting this equation to get L in terms of W. And what you'll see is I'm going to put that here. What's L in terms of W? And the whole point of me doing that is so that I have everything in terms of one equation, or excuse me, one variable, so that in my equation I'm only dealing with one variable. Okay, and that's what's going to end up happening. I want to use those two things to help me optimize and maximize this area. Now, what I'm going to end up doing is optimizing this, finding those critical values. So I put it into the area equation. I have my length, which I wrote in terms of W, like we said, 50 minus W, and my width, which is just W. Multiply those together and take the derivative, because I want to take that derivative area. My critical value location is what I need to find. So I set that equal to 0 and I solve for W, knowing full well that that's going to be a location of a relative max or min. In this case, I'm looking for an area that has a relative max. Okay, so I just have to make sure that that 25 is a relative max. Okay, how do I do that? I test points in the first derivative on either side. And when I do that, you'll see the numbers I get there. See that it's increasing as I approach 25 and decreasing as I come away from it. So increasing, again, increasing to decreasing gives me a location right there at 25 where I have a relative max, which is what I'm looking for. I'm trying to maximize the amount of area for this garden. Okay, so 25 works out to be the width of this, all right, which when I use that to find my length, which my length, remember, is just 50 minus the width, so 50 minus 25 is also 25 feet. Then I want, the question said, what's the maximum area? So I use those two dimensions, length times width, 25 feet times 25 feet, to get a maximum area of 625 feet squared. That's the optimal dimensions, right, width and lengthwise, to be able to get the most amount of area of garden based on the amount of fence that I had, which was 100 feet. Okay, and if you think about this, does that 25 feet, two lengths of 25 and two widths of 25 add up to 100? It does. Good way to check to see that you've met your constraint. Just plug that length and width back into the constraint and see that it still adds up to that 100 feet. All right, and in this case it did. I have optimized the amount of area for my garden. You'll see that I skipped example 2. I'll go back to it later. So take a look at example 3. All right, we have a box, a box that's already been constructed. Okay, it's got a square base. That's very important. Okay, because when I go to label my diagram already drawn here, the square base means that both dimensions on the bottom are going to be the same. That's important and key here, because it limits the amount of variables I have. Instead of having 3, a length, a width, and a height, that are all different as far as variables are concerned, I have 2 that are the same. So if I have x and then one other dimension, that's 2 variables, meaning that I will need 2 equations to solve it, which is good, because I'll have an optimization equation and then I'll have a constraint, as you can see over to the left. All right, so over here, what is my volume? How do I know that the volume is what I'm optimizing? Because in the end, it says find the dimensions of the container with the greatest volume. That means I'm trying to maximize the volume. All right, so that is my optimization piece. That's the one that I'm going to try and find either the max or the min of, and in this case, it's the max because it's the greatest volume. All right, what is my constraint? My constraint is basically the amount of material that I have given to me here, 1,000 feet squared of material. Feet squared should be a dead giveaway that that is an area. Okay, that is the surface area essentially of the box. All right, so how do I lay that out? Well, the 1,000 is my actual area that I have to work with. The x squared comes from the fact that, first off, this is an open top container. There is no material being used for the top, only for the bottom. So to account for the bottom's material, I have 2 dimensions on the bottom. What's the area of this bottom here? The area of the bottom is just x times x. So there's one bottom that's using up some of that material. And what is it using up? It's using up x times x. That's where the x squared comes from. The 4xy comes from the 4 sides that are also using up some of that 1,000 square feet of material. X times y are the dimensions of all of the sides. Okay, so if there's 4 of them with an area of xy, 4xy is included. There it is, 4xy in my constraint equation. All right, and are taken out of that 1,000 square feet of material. So I've got one bottom that's taken material, and I've got 4 sides that are taking material, and the top is not taking any because it's an open top, as it said in the beginning. Okay, so there is my setup for that problem.